All right, so last time, oh, you know what? Before I go over something from the lecture, did any of you guys have homework questions or whatnot? Yeah. The only thing I did want to mention is on, I believe, one of the problems it says to classify, say, the cycle structures of maybe one of the SN groups or the AN groups. Was that one of the problems? I just wanted to show you at least a sort of some kind of notation you could use. No, not that one. There's one that says like show what the cycle structures of SN or AN are. Is that one of the problems? Yeah, 11 from chapter 5. All right, thanks, Kelsey. Hang on a sec. Let me bring that up actually. Okay, so yeah, one thing I just wanted. Chapter 5, number 11. So what are the possible cycle structures of elements in A5 and A6? So one thing I wanted you to see, just for a, okay, so stop sharing that. Okay, so a trick that you could use if you, yeah, so if you want to, so for example, I could write a cycle like this. So for example, let's say 1, 3, 2, 5. Okay, so this is a 4 cycle. Okay, but if you're just talking about what the structure of a 4 cycle is, it pretty much has this structure, A1, A2, A3, A4, where these are some numbers. So that's one way that you could represent a 4 cycle. Another way that you could just say that I have a 4 cycle is you could just write something like this. Maybe put a 4 and maybe underline it and just say that this represents a 4 cycle. Okay. So in general, if you want to just represent an n cycle, some cycle of length n, but you don't know what the elements are. So it's kind of the same thing as doing this, but if you wanted to write it more efficiently, it would look something like this. So why would you want to do that? Well, for example, do you see that this one I could write, if I wanted you to figure out if that's even or odd, you'd have to write it in terms of its 2 cycle decomposition. And I did give you a trick for that, which is 1, 5, 1, 2, 1, 3, right? And so we would see that this is an odd element because there's an odd number of 2 cycles in its decomposition, right? So one thing you should immediately notice, well, in general, if you had an n cycle, then this would become, if you use this trick, it would become, it has a 2 cycle decomposition with n minus 1 2 cycles, right? Because using that trick, the one that I showed you in class, a cycle of length n would decompose into n minus 1 2 cycles, just like this 4 cycle decomposed into 3 cycles. So what that means is anytime you encounter an n cycle, then it'll switch parity. It looks like, well, the length will determine the parity, right? So if this was a 4 cycle, that would be odd. If it was a 7 cycle, that would be even, right? Because n minus 1 will be 6 there, all right? Okay, so I'm just mentioning this as sort of a shortcut notation. And if you look at the extra problems, so let me share the screen again. So you know how on our course page, I shared with you extra problems and comments. So if you go to this, I have a bunch of problems for chapter 4 and 5 here. And if you look under chapter 5, I give you some more computational examples that involve the permutations. So this would be good to look at when you're studying for the next exam. You know, the permutation group is very good at coming up with computational type questions. But then down here, here's a question. It says, what are the possible disjoint cycle structures of S6? Okay, so again, a quick shortcut is, well, let's denote a cycle of length n by just writing it like this, n with an underline and sort of parentheses. So a 6 cycle you could denote like this. And an example would be this. But instead of writing out all of the cycle, all of the elements, that would take a long time, right? I mean, 6 factorial, you would not want to write out all the elements. So instead, what you can do is you can sort of organize them into groups based on how long each of these cycles are, okay? So in other words, what you'd end up with is this, this collection. You would have elements in S6, they may be a cycle of length 6, right? Or it could be a cycle of length 5 and a 1 cycle, right? Or it could be a cycle of length 4 and a 2 cycle, and so on, right? What you're actually producing here is what's called a partition. You're partitioning the integer like into smaller integers whose sum would be 6 actually. But that actually gives you a cycle, the disjoint cycles. Does that kind of make sense? For example, I'm not saying that there's only one of this type. Like this right here is saying you have a 3 cycle and then a 1 cycle, 1 cycle, 1 cycle. There are many elements of that form, but I'm just saying that you're sort of organizing the elements into this type. And you could do that for any Sn. The nice thing about doing this is it gives you some idea of orders of elements, right? So for the next follow-up question, I ask, well, what are the possible orders? If you've already determined all the possible disjoint cycle structures, then the orders are going to be the least common multiples of these elements. So that's actually pretty quick once you figure that out. Another thing you can figure out is once you take this, you get this, I can decompose them into 2 cycles and figure out whether or not they're even or odd. So if you look back up here at what we had up above, I sort of explained, okay, an n cycle is even or odd. We kind of discussed that already, right? So if it was length 5, it would be even because that would become 4 2 cycles. If it was length 4, it would become odd because that would give you 3 2 cycles. But later on, then I say, okay, go back up above and look at whether or not you'd get even or odd. And so you see that the 6 cycle is odd because that would become 5 2 cycles. The 5 cycle and the 1 cycle will be even because that becomes 4 2 cycles. And here's the first interesting example. So let's say you have an element in S6 that's a 4 cycle and a 2 cycle. The 4 cycle would become 3 2 cycles, and then you'd have one more 2 cycle, which would give you a total of 4 2 cycles, right? So that would actually be an even element, okay? So you can use this sort of trick to classify whether or not you have even or odd elements, which means then that tells you what the structures of A6 would look like, right? They would be the ones that are actually even. So does that kind of make sense? The only way you could really solve that is by looking at all of Sn and then figuring out which ones are even and which ones are odd, okay? But so even doing that can take you some time. But I think I asked you for S5 and S6. So I kind of, is that what it was? A5 and A6? Hang on, let me stop sharing this so I can look back up. Oh, yeah, A5 and A6. So I kind of already spoiled the answer for A6, but see if you could redevelop it and check the answer for yourself. But A5, you should be able to do it using pretty much the same idea.
Yeah.
Okay.
I got a question on, I think it was first question on question 20. I'm not chapter 4, I think. Which was with the 4.
Okay. The very first one.
Yeah, question 20.
So list the 6 roots.
The second 2 parts of that. How to find the generator.
What are the generators? Yeah, so those are the ones. So okay. They're the same as the primitive roots, the generators. It's the same as those. So just, so for the sixth, okay, so remember mu n is generated by e to the 2 pi I j over n if and only if j and n are relatively prime. So the GCD of j and n is equal to 1. So for example, the first primitive root will always generate it for you. So 2 pi I over n is the first root. But if you're talking about mu6, it would be e to the 2 pi I over 6. And then I could replace that I with anything that's relatively prime with 6. So this will always be one generator.
The I or the J?
Oh, I'm sorry, the j that's right here. Yeah. So forget what I said there. Yeah. 2 pi I, and then we can't put 2, right? Because that, yeah. Yeah, 2, 3, 4, 5. You can only put relatively prime. So in this case, you only get 2, right?
Okay.
Is that?
Yeah, that, I think that makes sense.
Yeah. If you look at that geometrically.
How would you graph that?
Yeah. So if you go back to that lecture where we talked about how you graph these points, what you're doing is you're actually taking 2 pi and you're dividing it into n sectors, right? So for 6 points, you would have one here, one here, one here, one here, one here, and one here.
Yeah,
So it would be 60 degrees or pi over 3. Because if you look at that, that's actually pi over 3, right? 2 pi over 6 is pi over 3, which is, so this is pi over 3. And then another pi over 3 will get you over here. And then another pi over 3, another pi over 3. So this is e to the, well, it's really the 2 pi I over 6, which is the same as e to the pi over 3 I, right? And if you kind of think about it, if I take that and I multiply it by itself, so if I square it, remember you will, it's on the unit circle, so it's not going to go any further out from the origin, but it'll get you to the second point. And if I cube it to the 4th, to the 5th, and then to the 6th. So that's why this actually generates everything. But if I was here, if I started at this point instead, if I square that, then I would actually get down to this point down here. And if I cubed that point, I would end up at the origin. So you see that one will generate a subgroup of size 3, but it won't generate the whole group. And over here, I would actually be at it's -1, and the square of that will be here. This one, if I square that, so 1, 2, 3, 4, 1, 2, 3, 4, I would actually end up at that point. So if I started at this point and squared it, I would be here. And then if I cubed that point, I would actually end up at the origin. I don't know if you guys see that or not.
Yeah.
We
So
could,
for the fifth one.
but the 5th one is the only other one that'll actually generate all of them.
Yeah.
Yeah. Because it's like I got to move 5 points, right? So 1, 2, 3, 4, 5, right?
Okay.
Yeah. And if I square that, then I would be 1, 2, 3, 4, 5. I'd be here. If I cubed that one, then I'll be here.
Gotcha.
Yeah. It's not obvious, but this is it. This is
I remember when I watched the lecture, just kind of almost like ignoring the eye and looking at
the angles. Yeah. Yeah. You could do it that way too. Like you would have, what is that? 10 pi over 6. So 5 pi over 3. I don't know. You're trying to keep adding that angle to itself until you get to a multiple of 2 pi. Yeah. What were you gonna say? Sorry.
So in the book, I was trying to get the formula for the points. It was like CIS 2k pi over n.
Yeah, I did that in the lecture. I kind of just spoiled it for you and told you what it is. I mean, if you want to see how to derive it, it's from you have to take complex analysis.
Yeah.
But you're trying to solve this. You're trying to solve this equation, and it only will have at most 2 real solutions, right? If n is even, -1 and 1 will be solutions to that. But if n is odd, there'll only be 1 real solution, and then the rest will be complex. But the complex solutions always come in conjugate pairs. So you see that reflecting it over the real axis, you'll always have the conjugate pairs. The cool thing about this is you'll always end up with the vertices of a regular n-gon inside of the unit circle. So those are all on the unit circle, and they should be the vertices of a regular hexagon, right? 6-gon. Yeah. Okay. Well, hopefully that helps a little bit. If you need any more hints, just let me know. I can email them to you, or we could talk about them again. But for the most part, it's going okay. Yeah. Or anybody that's online that has any questions too, just let me know. Okay.
Is there a note packet? What's there?
Yeah, I printed one, but I think we're gonna have enough to get through the coset stuff from last time.
Okay.
The cosets. Do you still have that one?
Yeah.
Yeah. Yeah, but there's a lot of stuff there. So yeah. Okay. So last time we started talking about cosets, right? So you should think of a coset as you have a subgroup. It's kind of like this. So you have a group G, and then you have a subgroup, okay? And what these cosets are doing is it's sort of translating the group, okay? So you're getting these new collections or sub-collections of the original group, okay? So you have a subgroup, and this is the only one that has the identity in here, okay? So this is the only one that will be an actual subgroup, but the cosets are giving you other pieces of the group, and they have certain properties. That's kind of what we wanted to talk about today. So one of the properties that we did notice by doing these examples of calculating these things is the cosets seem to all have the same size. So that could be useful. And they also seem to form a partition. So what that means is they should not intersect. Every element is represented. Okay, every element of the group is in one of these cosets. And they're non-empty. So every coset has to contain something. Okay, and they also have other properties as well. Bless you. Okay, so let's see what properties we have. Now, this list, I really liked this list. It actually comes from a book by Joseph Gallion, so I'm referencing that. In your book, this is sort of scattered throughout, but I just wanted to create for you a nice organized table, and this one's pretty good. Okay, so the only assumptions we're going to make here is that we have some group, and H is a subgroup, and A and B are just elements of the group. Okay, the very first thing is that any element A has to be contained in the coset that A generates from the coset of H in G generated by A. Okay, so A has to be in that coset. All right, now the proof of that, what I left down here was room so we could try to prove these things. Okay, so all right. The proof of this is not terrible because since you have to have the identity in H, right? Since H is a subgroup of G, do we all agree that it has to have an identity, right? Well, what are the elements of this coset AH? They're things of the form A times anything in H. Well, since E is in H, then I hope we agree that A is definitely equal to A times E. That's just by definition. And this right here is A times something in H, right? A times something in H. So I could just say right here that this is an element of AH. Right? Remember, AH is a set of things. If you look back at this definition, it's a set of things that are of that form, A times something in H. So as soon as you get something in that form, right, A times something in H, then you could just write that it's an element of that set. So pretty short proof, right? That's all you need to prove that. Okay, what's the use of that? Well, that's actually showing you that every element is in some coset. So those cosets are definitely non-empty for one thing, and everything is going to be represented in some way. Okay, second thing, did you remember that sometimes we actually had that the coset that you calculated turned out to be the actual subgroup? So I wasn't actually shifting the subgroup in any way. And it turns out that that's going to happen if and only if A is in the subgroup itself. Okay, so this is an if and only if condition. Let's see if we could prove that. Okay, so let's prove this direction first. Okay, so prove this direction. So suppose AH is equal to H. So this coset is actually equal to the subgroup. And then what do you want to show? You want to show A is an element of the subgroup. Okay, well, do we agree that A is equal to A times E? Okay, well, what's so nice about A times E? That's an element of AH, right? And what do we know about AH? The assumption is that that coset is actually equal to H, right? And what are you trying to show? You're trying to show A is an element of H. So you actually just showed that, see, i.e. So in other words, A is an element of H, right? So you just kind of cleverly rewrote it. So I know that it's an AH, but the assumption is that that coset is actually equal to H. So therefore A is in there. It's really not too much there. Okay, now going the other way is going to be a bit more work, because going the other way, let's write out what we're going to assume and what we're going to show, right? So 2 up here, I'm going to say, suppose A is an H, and then what do you want to show? Yeah, AH equals H. Now, what are the proof techniques for showing these two things are equal? Well, this is a coset and this is a subgroup, right? So you're, in terms of showing they're equal, you're just showing that they're equal as sets, right? A coset is just a set, okay? And in order to show a set is equal to another set, a common technique is to show subset inclusion both directions. So that's why this one's just a little bit more work, because you have to do both directions there. Yeah, so to show this direction, i.e., let's show first that AH is a subset. I hope I didn't say subgroup. So they're sets. We're going to show that this is a subset of H. You don't have to do any 3-step thing here. We're just showing that it's a subset. Okay. All right. Keep in mind, you do have one assumption that A is an element of H. Okay. All right. Well, what could we do? You could do this a couple different ways. One way is you could just start by saying, yeah, pick something in here. Let A times little h be in AH, right? And then what do you want to show? Now you want to show that this element is in big H, right? Okay. Now what do we have to work with? We have that A is in this subgroup, and now we have AH is in this coset.
Well, we could let that little h be the identity again, and then we have A is an element of AH.
Okay. I should say that this is chosen in general, right? So when I say let AH be in this coset, that actually has to be a general element. So what you're saying is an example of such a thing, but we have to do it in general. So by writing this, so this is, notice that this is a general element, right? So how would I say this is for some little h in H, right? You could say that if you want. And that keeps the fact that this is general. And hopefully you see that that's useful to us, because I assumed that little a was in the subgroup, and now I know that little h is in the subgroup. So what would a times h? Yeah, because of closure, right? And so you could just say something like that. So since both A and H are in the subgroup big H, we must have A times H is an H by closure You probably could get away without writing so much. One way you could do that is you could actually just simplify the definition of that set as well. Like A times H is AH, such that H is an H, and then you could say, oh, well, that has to be a sub. Yeah, you could get away with like saying that thing is a subset of H a couple different ways. But I think that that's probably a nice way to write it out as a sentence to remind you of this. We good so far? All right, now let's go the other way. So now you're going to show H is a subset of AH. H is a subset of AH, right? So I'm showing the subset inclusion both ways. So now I'm going to show the set on the right is a subset of the set on the left. Okay. Now this seems a little bit more complicated because how would you do that? You would say let little h be an H, and now you want to show little h is an element of AH. Okay. And it seems to me a little bit more complicated to show something is in the coset rather than in a subgroup like the previous thing, because this has a more complicated definition. So if you're stuck where to even start, you might want to translate one of these things. Right now, I just know that I have this element and I have that element A, okay? So maybe say something like this. So show H, what would it mean for it to be in this coset? It would have to be something like A times something in H, okay? Yeah, H equals A, and then maybe we'll call it H prime, right? For some H prime in H. Okay. Remember that this thing, AH, that coset, is a collection of things of the form A times H, where H is in big H. But so that little h is changing, right? So I have to give that guy a different name because it's just some other element. Okay, so that's why that prime is there. Okay. So somehow I have to decompose this. Is there any clever suggestions on how we could do that? So somehow I'm going to start with H, cleverly decompose it so I have that it's A times something in H. Okay. Any ideas? This is where you might do some scrap work and you just try things. Okay. So one thing you could do is, well, I can say H is equal to the identity times H on the right or the left. Maybe that's useful. If I say that it's the identity times H here, one reason I might want to do that is, I'm trying to make an A appear kind of out of nowhere, right? And to make elements appear, this is where you can utilize the identity, because the identity, I could always rewrite that as any element in the group times its inverse. So here's kind of where you do the math magic of things appearing out of nowhere, right? So do you agree that that's equal to that? It's similar to like when you multiply by 1 in this fanciful way, and then the professor simplifies it into something that looks nothing like what you originally started with, right? So you're doing that here, just in a group, okay? And do we all agree? I mean, technically you have parentheses here, and then I could just rewrite that as A times this. Okay. And this is actually good because look, I have my original H. I'm trying to show that it's A times something in big H. And right now I have it A times this thing. And do I know what's in parentheses? Is that in my, my subgroup H? Do I know that? Yeah, if you kind of look at all the things we've assumed, we know that little a is in the subgroup and we know little h is in the subgroup. So actually, yeah, so the inverse will be in there and h will be in there. So it's kind of two properties, right? Inverses and closure. I think someone has to go around and clean the handles. That's why it always looks like there's somebody looking into the classroom. Yeah, and there's like a sign out sheet that they have to sign. I had to figure that out too because it always seemed like somebody was trying to. Yeah. So this is in H since A inverse is in H and by closure, right? So you could say something like that.
Well, we already assumed that H was an element in H, right?
Yeah, yeah. So by closure would be A inverse times that thing. Yeah. I mean, even if you wrote that this is in H by or above assumptions, I wouldn't take off anything. It's just making sure it's clear that you're kind of using inverses and closure, using two properties. Technically, you're also using associativity there. So you're using everything. And you could just say that this is an element, not equal, sorry, an element of AH, right? In A times something in big H. So, okay. So that was a bit of work, but all of this is telling you is that you know when your coset is just going to stay your subgroup. Okay. Okay. And then from that, you can start to prove some more general things, actually. Is there any questions right now? I think we've written everything correctly for the properties there. Okay. Let's see. Number 3. Some of these we're not going to prove all of them. They're kind of annoying. But number 3 is an associativity problem. Okay. This one is actually not that shocking, but if you follow the definition, you'll inherit this from the associativity of the group. This is just saying if I took the elements A times B and computed its coset, it would be the same thing as if I took this coset and then calculated what this new set would be. It turns out it would actually give it that same coset there. So it's an associativity property. Now, number 4 is what I was hinting at last class. So what does number 4 say? This one is similar to number 2. Number 2 here was saying that the coset you're calculating is the subgroup if A is a member of that subgroup. This one is saying that these two cosets are the same if A is an element of that second coset. So what 4 is telling you is as soon as you calculate a coset, all the elements in that coset would generate the same thing. They would not generate a brand new coset. Okay? So once you calculate a coset, all those elements in that coset will generate the same thing. Okay? So I guess let's write something for that. So this tells us when cosets are the same. So this is going to cut down the time when you're trying to find distinct cosets. Okay, so this is useful for this cuts down time when finding. If you were asked to find all the distinct cosets, this would speed up the process. Distinct cosets. Okay. Before we prove it, can I just show you from last class that we did see that actually? So if you look at this one, let's pick something that's not the identity, right? So these first two, ignore that. So this coset, if I took 1, 3 times H, I simplified it and I got these two elements, right? So the 1, 3 was in there, that's by that first property, but then I had this element 1, 2, 3. And so if you were asked to find all of the distinct cosets, I now know that if I wanted another distinct one, I would not use the element 1, 2, 3, because if I do, as I did right here, you'll actually get the same coset. So you see, it's just cutting your work down significantly. In fact, if your group was very large and your cosets were not too small, this would save you much more work, right? So the larger the subgroup, the more time this would save, actually, right? If your cosets were singleton sets, then this would not help you at all. They would just be single element subsets, and that wouldn't save you any time. So it would be really annoying. That would be in the worst case scenario. Okay. Do you want to prove that? You know what? Let's talk about what the remaining properties are, and then maybe I think some of these I might have given you for homework. I think number 4 here is a homework problem, and number 5 might be also a homework problem, but not this week, obviously. You know what I'll do is I'll think about whether or not we'll just prove all of them. But hang on. So what does 5 say? 5 is another way. What does this remind you of? You guys notice you've seen something like this? So this is saying these two cosets. All right. That actually made it worse. Never mind. Thought I was going to be able to use that zoom feature very fast. Okay. These two cosets are either the same or they are disjoint. So if you calculate two cosets, you're either going to get the same coset or they're disjoint. So in other words, that's the property of like in a partition, right? Your element. This is really just saying that cosets are disjoint from one another, okay? Or they are just the same thing, right? You're either calculating the same thing or you're getting some completely disjoint property. And that's fundamental to the property of getting a partition, right? Remember, if I give you a set, a partition on the set is you got to give me non-empty elements, non-empty subsets, which we did, and you'll have disjoint, and then the union would be the whole collection, okay? Which actually one kind of gives you both of those properties, because as soon as you know one element is in a coset, then you know that it's always represented, right? And you also know that they're non-empty. So one, even though that was the simplest one, is actually giving you two of the partition properties. Okay, so 5, this is just saying distinct cosets are disjoint. A sort of hand-wavy proof of that, you know, like what I'm doing with this pen here, is if you had something in the intersection, then this previous property would say that, okay, well, if I had something that's in the coset AH, then it wouldn't generate anything new as AH, right? And if I had something in the coset BH, then it wouldn't generate anything new from BH. And so then I'd have to have AH is equal to this CH, and that CH would have to be equal to the BH. So it would actually force this first property here. So you see, that's actually how you prove it. You're in either this condition or this condition, right? So if I suppose I'm not in this condition, there's something in the intersection which will actually force that first condition. So it actually follows from 4. Might not seem like that, but it does. Okay, 6, what is that telling you? It's just another way of kind of saying 4. So it's not really, it tells us when cosets are the same in another way, but this one is much better, right? 4 is better at doing that. They're 4 and 6 are kind of doing similar things. It's just you're writing it in a different way, that's all. Okay. 7 is going to be very useful for us. This one is telling you that cosets always have the same size. Okay. All cosets have the same size. Cardinality in general, right? So even if this is infinite, they would have to have the same cardinality. Okay. So each coset has the same size or cardinality. For finite groups, that's going to be very useful for us. Property 8 here is actually quite useful. It looks a little weird. This one is actually saying when the left and the right cosets are the same. So this is saying that the left coset of A is the same as the right coset if and only if this condition is held. Okay. Now, what the heck is that set? I never defined that. So let me define that for you. You can probably guess what that definition would be. remember how AH was defined as A times little h, right? This one is A times little h times A inverse, such that little h is in big H. Okay. So to summarize, this is saying the left cosets, the left and right cosets are the same if and only if, so it's actually a if and only if condition, H is equal to this special set here. Special set. Okay. And that turns out to be quite useful. We will use that later on. Okay. I'm kind of leaving you on a cliffhanger here because we haven't really looked at the right cosets very much. I mean, you can calculate them. But if your group is abelian, the right cosets don't give you any new useful piece of information, right? Because they are going to be the same. But if you're in a non-abelian group, they are not necessarily the same. And it turns out that you can have a non-abelian group have the left and the right cosets be the same. And when that happens, something really significant is happening with the subgroup that you're using, okay? Because think about this. To create a coset, you have to have a subgroup, right? Okay, so in order for this property to hold, something very significant has to be happening with this subgroup. So it's not only a group property, it's sort of a subgroup property. Okay? Something special is happening. Okay, and we'll talk about that. We'll actually say that that subgroup is called a normal subgroup when that happens. And the word normal in mathematics is probably the most abused word ever because 1,000 things in mathematics are normal or regular. Those are the two worst. And if you've taken topology, you probably have noticed that as well. Because talk about
standard
yeah. Yeah. Okay. And then AH is a subgroup if and only if A is in here. And that last condition really just follows from number 2 there, right? Because the only time that you're going to even get a subgroup is when your coset is equal to H, because that's the only one that has the identity in it. Yeah. Okay. So we will use 8 again, but not until later, and we'll come back to why in the world would you care about such a situation. 7 we're about to use for the results on the next page, and then you'll probably kind of not think about that again. 4 is useful in terms of computing these distinct cosets. So 4 is pretty useful too. Okay. These other properties are going to be kind of hidden behind the scenes. Like this one is somewhat useful. Okay, let me try to rank these in terms of importance. So these are pretty important in terms of proving the next page. This is only really useful for calculating distinct cosets. And then right now, this one is the weirdest, but that one is also going to be one of the most useful. So this is a completely biased ranking system that I just came up with on the fly right now, but I think that's probably accurate. Are we okay so far? A little weird, right? I'll probably end up showing you how to prove 4 and 5. Okay, but maybe let's move on to see, okay, you have these cosets and they have these properties, but why do we care about them? All right, so let's try to answer that. And the answer is this theorem, okay? So far I've given you the first punchline of this course, I would say, is the fundamental theorem of cyclic groups. And then I would say that I would call this the fundamental theorem of finite groups in a way, but let's just call it Lagrange's theorem because we're only going to refer to it as that. So this is like the second punchline in the course. Okay, so you're going to use this a lot. Okay, so what does this say? The first thing is the most important. Okay, so this says if you give me a finite group, keep in mind everything I'm talking about here is not going to work for infinite groups. Okay, so the group is finite, H is a subgroup, A is some element, and P is some prime. So the very first thing is saying that the order of a subgroup must divide the order of a group if it's finite. Okay, so you can write that out if you want. The order of H must divide the order of G. Now, in all of our examples that we've done, we sort of hinted at that, but we had no proof of it, right? The only groups that we knew that so far, absolutely knew it, and I didn't actually prove it to you, was the cyclic groups, right? Cyclic groups, you actually are not only guaranteed this, you're actually guaranteed you have subgroups of all those orders, okay? So this is not actually guaranteeing you have a subgroup of each divisor. It's just saying that if you find a subgroup, the order of that thing must divide the order of a group. Okay? So let's try to prove that. That's the main thing I wanted to prove today. Okay, and the proof of this is going to use cosets. So the real reason that we even cared about cosets is actually just to prove that very first property right there. Okay, so proof of 1. Okay, so the main tool we're going to use is cosets. Okay, and you're really not going to be able to just guess all of this. And there's a reason that Lagrange's name is associated to this theorem, because I mean, it was a pretty big deal at the time to actually prove this. Okay, so suppose that A1H, A2H, all the way up to, let's say, ARH, are the distinct left cosets of H in G. Does everyone agree that such a collection would have to exist from our previous properties? Every element of the group has to belong to some coset, and there are some distinct ones out there. There may only be one, but you definitely have to have a list of distinct left cosets. Okay, so everyone should agree that you should be able to do that. So a picture you could have in your mind is kind of what I was talking about before. You could think of your group as a cake, and these cosets are going to take slices out of this cake, okay? So you're going to have A1H, A2H, all the way up to ARH. Most likely, if you ordered this in a really nice way, this first one is probably actually going to be H itself. One of those has to be the subgroup, okay? So this one, let's just say for the sake of making the picture really nice, that one is actually the H, right? Okay, so here's a visual you can have in mind. Okay, now for every element, G in the group, okay, GH is got to be equal to AIH for some I. Does everyone agree with that? So remember that if I take the element G, I can just build its coset, GH, and G will definitely have to be in here. But from the properties that we have on the previous page, I'll wait until you guys are done writing. Okay, so just looking at these properties that we have, right? Looking at this very first one, this says if you take any element, it's got to be in the coset that it generates, right? So one way that I could try to simplify this a little bit, does everyone agree that G would be an element of that coset, GH, by that first property? Now GH has to be equal to AI for some I, because every single element of the group has to belong to some coset. Okay, it's kind of just saying these are all the distinct cosets. So every element of the group has to be in one of those pieces, right? So if I took the group and I divided into these pieces, every element has to be in one of them. That's all we're saying. So it's kind of a legitimate partition of the group. Okay. So what does that mean? So this means what does that mean? Well, G would be the union of all these cosets, right? So G would be A1H union A2H union dot 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 ARH. And in shorthand, some of you that have taken maybe analysis or topology or something, well, in discrete, I think I usually show this notation, right? You can kind of just shorthand that just like you did with sigma notation, but unions instead. Okay? So all these unions, okay? Okay, so G is equal to that union, but this theorem here that we're proving has to do with the order of G, and we're trying to show that the order of H divides the order of G. So now that I have this representation of G, can you compute the order? Okay, so what would the order be? Well, the order would be the order of this union. Everyone agree with that? Now, here's the really cool part. All of these cosets actually do not overlap anywhere, right? They share no common elements. So these distinct ones, so these distinct cosets are all disjoint, right? That was property 5 on the previous page. Okay. Now, what happens when you try to add up the cardinality of disjoint sets? Can I just draw a picture for you guys real quick? So, well, so here's two subsets, right? And the first one has 2 things, and the second thing has 3 things, and they're disjoint with each other, right? So let's say you wanted to compute the cardinality of the union. Do you see that it would actually just be the cardinality of A plus the cardinality of B? Okay. Yeah, if they actually did overlap, then you would actually have to subtract off the intersection. That's called the inclusion-exclusion principle. The picture would look like this. So let's say I had 2 things in A and 3 things in B, right? Then the size here of this union would be, you could say it's A, the size of A plus the size of B, but that's an overcount. So I have to subtract off the intersection because I counted that intersection twice. You see, I would count that point once from A and once from B. So I had to subtract it off once to deal with the overcount. This is called the inclusion-exclusion principle. You can actually generalize that to any number of sets, and you get this alternating sum. Okay, but if it's disjoint, do we agree that it's actually quite simple because you just have to add them up and you have no intersection, right? This is empty. So it's actually as if you still have that, but this is 0, right? Because the intersection was empty. So what does that mean? This size of this union just turns into a sum of the cardinalities of these cosets. That's what's kind of cool. Okay, so this actually just becomes the sum of the sizes of these cosets. If you don't like the shorthand, you could just write it out in longhand. You would see that this cardinality would be the sum of the individual cardinalities, which would be this. Okay. In general, if they were not disjoint, you would have a sum like this, and then you'd have to subtract off the sums of the intersections, and then you have to add up. That would be pairwise, and then there's triplicate, and so on. So if you ever take a prob stats course where they do that, it's kind of horrendous in general, the more general version. Okay, but they have no common intersections anywhere. All right, so far I have written that the order of G is the sum of these numbers. These are just numbers, actually, right? The cardinalities, right? Why is that useful? Is there another property on this collection here that has to do with cardinalities? Yeah, they're all the same size, right? So number 7, every coset has the same size, and one of those cosets has to be the size of H, right? Because there's got to be one coset that's the same as H there. So check this out. So now by property 7, these all have the same size. Okay, so AIH is equal to AGH, which is, do we all agree that, for example, I could have picked the element E in the group, right? E is in one of these cosets. So do you agree that this is equal to EH for some element of the group? I'm going to pick E. Well, then that means that's just the size of H. Okay. We're getting somewhere, right? So this is still the cardinality of G. And now finally I have the cardinality of G is this. Well, what is that? That's yeah, that's just R times H, right? This is cardinality of H plus the cardinality of H plus dot 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 plus cardinality of H, total of R times. So in other words, I have this is equal to R times the cardinality of H. Okay. So I'm actually done. Do you see that the order of this is a number, must divide G, right? It's a factor, okay? So it kind of, and we give this thing a name. This R here is called the index. This is called the index of H in G. Okay. C2 above. Okay. So you actually just proved that if you have a subgroup, that the order of that thing must divide the order of G. And the inner workings of how you proved it was this tool. So right now, cosets were kind of just this tool to make Lagrange's theorem work. We will use it again for other things, but it's kind of, you built this tool to then be used to prove this sort of significant result. Okay.
Oh, cool. I didn't know where you were going at first.
Yeah, I mean, they seem pretty useless at first because you're just kind of taking the subgroup and then building these random sets. Okay, but if you look back at your original picture up above, what this is kind of saying is if you have a group, you think of it as a cake, and you cut based off of that subgroup. So the subgroup is going to take a certain proportion of that cake. What that's saying is that is the nerdiest way to cut a cake. So it's a fair cut, right? Because you will get the same size and you will end up with no remainder. You see that it'll be perfect, right? You won't. If you had a remainder, then that would mean that it's defying the this condition, that it's a multiple, right? You'd have a plus or remainder. Like the order would not be just the size of this plus this. So it's the nerdiest, most fair way to cut a cake. Okay? So the subgroup must be a divisor of that thing.
Makes sense.
Yeah. We should bake a cake and write this stuff on it sometime. Okay. Yeah, I know, right? But the Pi Day always ends up like on a weekend or something.
Yeah,
Well, not always, but it seems to have. Yeah. A lot of times it's also around the break too, right?
Yeah, I miss spring break. It's about next week, I think, should be spring break that we take.
Yeah.
So we'll be here.
So 2 here, 2 is just saying if you compute the order of G over the order of H, which we now know must be an integer because the order of H must divide this. So this would be an integer. We call that the index. Well, what would that represent? This would represent the number of distinct cosets that you have. Because you remember the way that we kind of broke this up, we said that there's R of these slices, right? So in other words, that R right here. So if you compute R, right? R is equal to this, is an integer. It's telling you how many slices that you actually have, right? How many distinct left cosets you have, okay? So that's one reason that you might be interested in this, the index, okay? So if I asked you the question, say, compute how many distinct cosets you should have, that's pretty quick, but because you just compute this ratio. But if you, and it'll be an integer, but if you actually had to go and then compute the actual cosets, that'll take a bit of time, but you could at least check yourself, did you get the right number, right? Okay. Okay, now, once you have Lagrange's theorem, you can prove all these other things for free. For example, one thing you can immediately prove is not only do subgroups have to divide this, elements have to divide this. Okay, so if you give me any element in the group, it has an order and it must divide the order of a group. Okay, and the proof of that is actually extremely short. Okay, because we had this random property that I mentioned before. So the proof of 3 is, recall on one of those index cards you probably made, that the order of an element is actually the same as the order of the cyclic subgroup that A generates, right? Recall that this was actually a little lemma that we had, okay? Well, this thing is a subgroup, but this is a subgroup of G. So what does that mean? We can use 1. And so this divides the order of G. Well, that is, these are equal to each other. So that is the order of A divides the order of G. Okay. Okay. The next property is saying if the order of the group is prime, then it turns out that the group actually must be cyclic. So that's pretty strong. So yeah, any prime you want. So I'm not talking about Zn, right? Zn, you know that all of those are cyclic, and Zp, for example, is cyclic. But if I give you any group with prime order, so for example, what's something that we didn't know was cyclic? For example, the UN groups are not always cyclic. Sometimes they are. So if you find a UN group with a prime number of elements in it, it must automatically be cyclic, and you don't actually have to find the generator, unless you're told to, right? Okay, so the proof of that, right? So this is, we're proving if a group has, where P is prime here, right? That's up here. So P is a prime number. So make sure you realize that we're only talking about prime P. Okay, so let A be a non-identity element. Okay, then by 1, the order of A must divide the order of the group, which is P, right? So the order of the group must be divisible by this. But what does that tell you about the order of that cyclic subgroup? If it has to divide a prime, what are the only possibilities?
1.
Yeah, 1 or P, right? Right. The only divisors of a prime are 1 and P. But P only has divisors 1 and P. Do we agree with that? And A is not the identity, so it can't have order 1, right? So that means it must have order P, which means the order of this cyclic subgroup must be P. And if you find the order of the cyclic subgroup is P, but that's the same as the order of the group, then that cyclic subgroup must give you everything in the group, okay? So that means that this must be the entire group, actually. Which means that G is cyclic, i.e. G is cyclic. The last property is just saying, the last property up here is saying, and this is all multiplicative, but if you took an element and you raised it to the order of the group, then you would definitely have to get the identity. So what that means is you have an upper bound on this thing. You can't, like if I took anything in, I don't know, mu n, right? Let's say you took something out of mu 2020, right? Pick any element in there. If you raised it to the 2020th power, you're absolutely guaranteed that has to go to the identity, which is 1. Okay. Yeah, you could do it much sooner for most elements. And the reason for that, and that's part of the proof actually, the proof of 5 is if I take this, okay, I can decompose this into A to something. Okay, let me see if you guys can fill in the blanks here. So to something. So what I'm going to do is I'm going to have a product of two numbers here, and these two numbers will be here because of properties of exponents, right? But I want this to be the identity. And now the identity to anything is the identity. So all you got to do is fill in the the crossword, right? That'll never exist, right? Or fill in the blank that'll never exist. Looking here, if you took A to the power of something and you got the identity, what's one thing that should come to mind? What is one instance where that would happen? A to what power gives you the identity should ring some bells. So okay, the number I'm looking for here, okay, that's a good guess, but I mean technically that is correct, but what I'm looking for here is something that's a positive integer. Okay, so that is the order of the element, right? Yeah. So if you raised A to the power of its order, do you agree that that would be the identity?
So if you raise it to A,
okay.
It's order times 1 now.
Yeah. So the order of this times something.
It doesn't matter what it is.
It doesn't matter. All I know is that this is actually some integer. You see that? And how do I know that? This is some integer. Yeah. We just proved in property 3 here that the order of every element divides the order of G, right? So you're actually guaranteed that the order of A divides the order of G. So this must exist, right? This is for some integer, K, and this is guaranteed by 3. Sorry, 3. Does everyone see that? It's sort of this silly, clever trick, right? And this is still K, and this is still K, and you get it. Okay, now another thing I want to point out, this does not say that the order, note, this does not mean the order of A is the order of G, right? Because you remember I told you that if you take an element, you raise it to the power of some number and you get the identity, that does not mean it's the order of the element. It means that that order must divide that number, right? It could be, like for example, if I told you A to the 6 was the identity, it could be that the order is 1, 2, 3, or 6. I kind of talked about that a little bit in the lecture that we were talking about order. So look back on that, and that'll come up in the homework that's due this week, right? Okay. I mean, property 5 is not extraordinarily important. It's kind of just telling you that there's an upper bound on the order. You can't have that the order goes beyond the order of the group, okay? Now, one other thing I want to note, so as a big warning, and it's a sad warning because it would be cool if this actually was true. The converse of Lagrange's theorem is not true. Okay, and what I mean by that is, do you see that this is saying if here, let me write this. So Lagrange, if H is a subgroup of G, then the order divides this, right? This is finite, right? This is for finite groups. Okay. So just ignore infinite groups. So for finite groups, Lagrange is saying this: as soon as you tell me that I am a subgroup, then the order of this must divide G. So it's pretty significant. It's really nice. But what would the converse be?
H divided, order of H divides order of G.
Yeah.
H is the subgroup of G.
If let's say if K is a divisor of this, then must there exist a subgroup H with this order? Okay, and the answer is no. Okay, so, and that was actually an unsolved problem for a long time. So people tried to see whether or not this was even true, and then this was an unsolved problem. I think it was proved by Ruffini in like 1799 or something like that. So it was unsolved for 9 years, but it was unsolved for even longer than that because people were wondering whether or not you could construct such a group for a while. Like the idea is, can you construct a group that does not have, okay, let me kind of spoil it. There exists a group of order 12. This is the smallest order where this happens. There exists a group of order 12 with no subgroup of order 6. Okay. It might be 1799, so it was actually even longer. I wonder if I have the year here somewhere. Yeah, 1799. So it was unsolved for a while, right? So even Lagrange didn't prove that. Okay. And it's actually A4. It's actually A4. You remember that the order of A4 will be 4 factorial over 2, which would be 4 times 3 times 2 over 2, which is 12. Okay. So if Lagrange's had a converse, then it would say, just like the fundamental theorem of cyclic groups. So going back to this converse, can I ask you, is this true for some type of group? So if I knew that I have a divisor, then must there exist a subgroup? We know one family for which this is true, which is a subgroup. Okay. So, I mean, a cyclic group. Okay. So if I also know that G was cyclic, then this would actually be true. Okay. But for non-cyclic groups, it turns out that it's not true. Okay. And the smallest such example is of order 12. Okay. Beyond 12, it grows the number of non-examples, but okay. So it's no in general, but yes if cyclic. Yes if G is cyclic. Because do you remember, yeah, we talked about this, the fundamental theorem of cyclic groups. Remember, that one says as soon as you know the order of G, there must exist subgroups of each divisor of G. Remember that? So this is sort of, the fundamental theorem of cyclic group is sort of like an appetizer to Lagrange's theorem, because once you knew it for cyclic, then the question is, okay, well, what about arbitrary groups? The best you can do is just say that you can narrow down the possibilities, but you can't say you can't say whether or not you actually have them. Okay, yeah. So we've reached the end of the time, but yeah. So this does leave the door open for a lot of different things that can happen. Okay, if the answer was actually yes, then it would be much easier to kind of classify groups. They must have some significant structure if that always was a yes, but it is yes sometimes. And in fact, you can say it's yes in other situations, but you have to know more about the group. Okay. So work on the homework. I'm pretty sure that's due Friday, right?
Yeah.
Something like that. Okay. And let me know if you guys have any questions. All right. Use those extra problems to help you. I solved a bunch of them for the previous times I've taught the course. And in fact, I think a couple of them are actually homework questions. Some of the ones that I solved. Okay. So I will see you on Monday, right? It's Wednesday, right? Cool.